All right, y'all, welcome back to another exciting round of chemistry notes. In this video, we're going to talk about scientific notation. Probably you're pretty familiar with this, but you might just need a little refresher on what exactly it's supposed to look like and how to go back and forth between scientific and standard notation. So let's go ahead and get into it. The purpose of scientific notation is actually not to make your life harder. We use it to make your life easier by making very small or very large numbers easier to handle by using powers of 10. So remember, when something is written in scientific notation, it's going to be in this general form, some number times 10 to the some other number. And we're going to go ahead and talk about how to fill in these blanks here. So when you are converting to scientific notation, there are 4 steps to remember. The first step is to move the decimal point of the quantity expressed in standard notation right or left until there is only one non-zero digit to the left of it. So you're going to move your decimal point around until it is just to the right of exactly one non-zero thing. Remember, non-zero is 1 through 9, any digit that's not 0. That's step 1. Step 2 is to use the number that results as the coefficient. Which we call m. So once you've moved your decimal point around until you have something point something something something, this whole number out front here becomes the coefficient. Step 3 is to count the number of spaces that you moved and call that number n. And n becomes the exponent of 10. So if you moved your decimal point 7 spaces, then you would have an exponent of 10 right here. If you moved your decimal point 23 spaces, you would have an exponent of 23. This is your n value in this box. And then step 4 is just to make sure that everything is in the right place. So your final quantity should be expressed in the form, that coefficient m, times 10 to the n. Where again, this is your coefficient. This is not a 0 here out front. And this is telling you about the number of spaces you moved the decimal point. Just a quick note. I think it says it's a step in your notes. It's just something to pay attention to. You want to make the exponent negative if the decimal moved to the right. So if you had a number like 0.0003231, then we're moving our decimal point to the right here. That becomes 3.231 times 10. Because we moved our decimal point to the right, that's going to be a negative exponent, a negative 4. So rather than remembering that exact rule, something that I think is a little easier to remember, if you have a large negative exponent, it came from a very small value. It came from a 0 followed by a lot of zeros. So many zeros before you actually got to non-zeros. That's because you had to move the decimal point a lot of spaces to the right. So that large negative exponent comes from moving a lot of spaces to the right. Also, when you are converting back and forth to scientific notation, you should start and end with the same number of sig figs. Sometimes that means you're going to have to throw a 0 in there just to make it work. Just be aware of this. Be smarter than your calculator. And let's take a look at what this looks like. So here are some examples. We're going to change the following between scientific and standard notation. So let's take a look at some examples here. Letter A gives us 8,800,000,000 meters. Before we do anything else, let's just keep track of how many sig figs we're starting with so we know that we are ending with the same number. Here we've got 2 non-zeros, so these are definitely going to count. And then we've got all these trailing zeros. we are not explicitly given a decimal point. So none of these count as significant. And we are dealing with 2 sig figs here. So when it's all said and done, we should still have 2 sig figs. That being said, we are going to have to remember that there's an implied decimal point right here. If you don't see it, it's implied just to the right of the last digit. So now we're going to move it until it's over here because we want this one non-zero to the left. We'll move it 1, 2, 3, 4, 5, 6, 7, 8, 9 spaces. And we'll end up with 8.8. So we have that one non-zero out there, 0.8 times 10. We moved it 9 spaces and we moved it left. So that gets to be positive. Again, it's a real big number. It's going to have a positive exponent. And then always remember your units. It was meters, so it's still meters. And we had these 2 sig figs here and these 2 sig figs here. This times 10 to the 9th portion does not count towards sig figs. So we are all good there. Let's look at our next one. B is 0.00015 kilograms. This is a really small number, so we should end up with a negative exponent. And counting our sig figs here, we've got some leading zeros. Remember, those never count. We have 2 non-zeros, so we have 2 sig figs here as well. So moving our decimal point to the right, we're going to move it 1, 2, 3, 4 until it's right there. We'll look at 1.5 because we want that one non-zero to the left. 1.5, which is 2 sig figs, times 10. We moved to the right. We started with a very small number, so that should be a negative 4. And like always, units are kilograms, so we have 1.5 times 10 to the negative 4 kilograms. And that's our answer to this one. Looking at our next 2 examples, here we have them given in scientific notation, and we are going to put them in standard notation. Now, you can either remember that with a negative exponent, you're going to have to move to the left. To me, that gets a little confusing. I get the rules mixed up. But I just like to remember that negative exponents come from little numbers. I want to make this a little number. This is a positive exponent. I want to make this a big number. So I'm going to pick up my decimal point here, and I'm going to make this number smaller by moving to the left. I'm going to go 1, 2, 3, and 4, and I'm going to put it back down. I can even fill these in with zeros. I will end up with 0.00019 meters. Again, I started with 2 sig figs. I'm ending with 2 sig figs. All is good. And last but not least, letter D down here. We have 2.01 times 10 to the 3rd kilograms. Again, we are starting with non-zero, sandwich 0, non-zero, 3 sig figs. We should end with 3 sig figs. And this positive exponent means we're going to have a big number, so we're going to move the decimal to the right. We'll move it 1, 2, and 3 spaces. And that becomes 2010. Counting up our sig figs one more time. Non-zero, sandwich 0, non-zero, trailing 0, but the decimal point is gone. So we are all good. 2010 kilograms. All right, let's look at a different type of practice, which is comparing this exponent issue. People tend to have issues with this exponent and how it works. So we're going to determine which value is larger in each set of numbers. In letter A, we have 6.93 times 10 to the negative 8th, or 6.93 times 10 to the 2nd. So this is a bigger number. 8 is bigger than 2, but this is a negative 8. Remember, big negative exponents, very negative exponents, are very small numbers. This is 0.000000693. Might have miscounted a little bit, but essentially these are the same thing. This is real small. Over here, we've got a positive exponent, which means this is actually 693. So this is much bigger. This is our larger value. And if you need to write this out, you can, but sometimes the exponents get a little harder to have to count out all those zeros. So just think about very negative exponents are very small, positive exponents are bigger. So here in our next one, letter B, we have 2.4293 times 10 to the 36th, or 2.4293 times 10 to the negative 12th. So here we've got negative 36 and negative 12. This one is more negative, which means it's more small. That's how we talk now. This one is less negative, so it's less small. And another way of saying less small would be larger. So this is our larger value. Please don't talk like this. This is smaller, and this is less small. All right, let's look at another example. Letter C, we have 7.12 times 10 to the third, or 1.363 times 10 to the 12th. Take a second, see if you can get there on your own, and then watch forward for the answer. Try letter D as well. All right, in letter C, we've got 7.12 times 10 to the third, or 1.363 times 10 to the 12th. Well, here we've got 10 to the third, here we've got 10 to the 12th. They're both positive, but this one is more positive, and more positive makes it bigger. Letter D is a little different. Letter D, we have 10 to the third and 10 to the third. So now we do need to look at the coefficients. The only time the coefficients matter is if the exponents are exactly the same. So then 2.01 versus 5.19, well, this is bigger. All right, so now you'll have a little bit of room in your book to practice on your own, going back and forth between scientific and standard notation. Take a minute, try it out yourself. There's 1, A through F, and then on the next page, 2, A through F, and 3, A through F. And all of the answers are on the next slide, so don't move forward until you're ready to check all your answers. All right, a lot going on here, so make sure to check all of your answers thoroughly. Make sure you got what you needed to get. Hopefully you did, or at the very least understand why this is what you should have gotten and you know what you did wrong so that you won't do it again later. If you are still struggling with this, go back through, do some more practice, come into tutorials. More than happy to help you out. But again, it's a good skill to have going back and forth. The very last thing we need to talk about in this video is how to type scientific notation into the calculator, because this is one of those things that seems very easy and is actually pretty easy to do incorrectly. Then all of your work is right, but your answer is wrong, and we're all very sad. So please pay attention to how to type your scientific notation into your calculator. To be fair, there are lots of ways to do it. I'm going to recommend you use exactly one way. That is a method that replaces the whole times 10 to the with E. Not just any old E, a very specific E. This is going to be the safest and most efficient way to use scientific notation on your calculator. So when you're typing it into your calculator, what it's actually going to look like is, instead of 6.02 times 10 to the 23rd, it's just going to be 6.02 E23. This whole section, the times 10 to the, it's all gone. Please, please do not try and type something like 6.02 E 10 to the 23. This is something that people have a tendency to do, and it's, oh my gosh, it's so wrong. Please don't do this. This is saving you so much time. You just have to write the coefficient, and then the E, and then the exponent. That's it. No extra keystrokes. And the way to get this E is by typing second, hit the second button, and then hit the comma button, which see if I can draw a decent comma. It's not a good comma. Hit the comma button. It's right above your 7. Second comma will give you E. There are 3 different E's on your calculator. Please use the correct one. So let's put this into practice here. We are going to carry out the following operations, express the results in scientific notation with the correct number of sig figs and correct units. So problem number 1, here we go. We have 7.20 times 10 to the 3rd centimeters times 8.01 times 10 to the 3rd centimeters. When you type this into your calculator, you should be typing 7.2 second, comma, oh, it's a really bad comma, 3 times 8.08 second, comma, I'm really good at drawing commas, 3. These are the keys you should hit. What shows up on your screen should be 7.20 E3 times 8.08 E3. This is what it should look like on your screen as you're typing it in. And if it does not look like this on your screen, you are doing something incorrect. Please check what you have done. After you type this in, your calculator is probably going to spit out, or it should spit out, 5.8176000 as your answer. Well, we need to express this in scientific notation and with correct sig figs. This is a given. I don't have to ask you for correct sig figs. You should just start answering in correct sig figs and correct units. Well, you can actually do those first 2 steps in either order. Let's go ahead and just put it in scientific notation. If you want to round it first to the correct number of sig figs, you can do that as well. So we've got our imaginary decimal point over here. We are going to move it 1, 2, 3, 4, 5, 6, 7 spaces to end up with 5.8176 times 10 to the 7th. However, this is not the correct number of sig figs. Remember, the only sig figs we care about are these and these. So here we've got 1, 2, 3. Here we've got 1, 2, 3. Our answer should have 1, 2, 3, 4, 5. This is not okay. So we're going to cut it off right behind this 1. 7 says to round up. So we will get 5.82 times 10 to the 7th. And at this point, maybe you're patting yourself on the back. Good job, me. I got my answer. There are no units. Your answer is wrong. Remember to include your units. When you do centimeters times centimeters, it's going to give you centimeters squared. So that is our final answer. 5.82 times 10 to the 7th centimeters squared. Let's do another one. Our next one here is addition instead of multiplication. Please remember your addition sig fig rules. And again, to type this in, we're going to type 4.74 second, comma, 3 plus 7.71 second, comma, looks like a G, 3 plus 1.05 second, comma, 3. And what shows up on your screen needs to be 4.74 E3 plus 7.71 E3 plus 1.05 E3. And if that is in fact what you have typed in, you can go ahead, hit enter, and your calculator is probably going to tell you something like 135 This is not in scientific notation, so let's go ahead and do that. We'll pick up our imaginary decimal point and move it 1, 2, 3, 4 spaces to the left. So that'll become 1.35 times 10 to the 4th. Now, quick sig figs check. Remember, since we are adding, we care about where the sig figs are. Our last one here was in the hundredths place, hundredths, and hundredths. So our answer needs to be in the hundredths place, and that's already done. Good job, us. So the last thing we need to do is add some units to this. We were adding kilometers together, so our units for our answer should also be kilometers. And that is our answer to number 2. Hopefully this is making a little bit of sense because it is time to practice on your own. Go ahead, pause the video when you're ready to check your answers to the next 3 practices. Go ahead and press play. All right, hopefully this is what you got. If not, there is a key up on my website. There's not a whole lot of extra work shown because there's not a whole lot of extra work to show, but it'll at least show you the middle step of exactly what you got out of the calculator and sort of what to do with that. So check that out if you need to. Go back over the notes, back over the videos. Head on over to your quest if you're ready. Get some of that done. Good luck and happy studying.